Good morning, friends. So we have continuation of laminar flow, what we discussed in the earlier class. So now the third equation is ratio of maximum velocity to uh, average velocity. So the velocity is maximum when r is equal to 0. As we discussed earlier, when we go away from the axis of the pipe, so that is small r is equal to capital R, the velocity becomes 0, but exactly at the axis of the pipe. So that is when r is equal to 0, the velocity is maximum. So we have from the previous equation, so we have my u is equal to minus 1 by 4 mu of del p by del x of capital R square minus small r square. So we have u max is equal to minus 1 by 4 mu of del p by del x into capital R square, substituting small r as 0. So this velocity equation we have arrived in the earlier part. The average velocity is now obtained by dividing the discharge of the fluid by cross-sectional area of the pipe. So that is pi r square. So velocity is now q by a. So for which we need to find out the discharge. Now consider a flow through a circular ring element of radius small r and thickness dr. The fluid flowing per second through the elementary ring is now given as dq is equal to, okay, here q is equal to av. So we have area of the ring element into velocity at the radius small r. So area of the ring element, as we discussed earlier, so it is the periphery of the uh, ring, so that is 2 pi r into thickness of the ring element, so that is dr. So it is 2 pi r into dr into velocity u. So we have substituted the u, that is the velocity, that is minus 1 by 4 mu of del p by del x into capital R square minus small r square into this area of the ring element, so that is 2 pi r into dr. Now Q, that is the total discharge in the entire pipe, will be obtained by integrating dq with the limit 0 to capital R, because here the radius of the elementary ring will be keep on changing. So the integration will be done with respect to this small r. So for which the integration limits will be 0 to capital R. The rest of the constant are taken outside the integration. Inside the integration, we have left out with this capital R square minus small r square into r dr. So integration of this r square into this small r. So radius of the pipe is not changing, so it is kept as constant. So it is integration of r square into small r. So keeping r square constant, integrating this small r, we are getting r square by 2. Then here we have minus of integration of r square into r, that is integration of r cube, we are getting r to the power of 4 by 4. So with the limit 0 to capital R. Then simplifying, we are getting pi by 8 mu of minus del p by del x into r to the power of 4. Now average velocity u bar, which is taken as the discharge q divided by area, because q is equal to a into velocity. So substituting q, what we obtain now here, and area as pi r square. So then u bar is, now we are getting this. Now we want the ratio of maximum velocity to average velocity. Maximum velocity, what we obtained earlier, we have substituted here. Average velocity, just now we got it, we are substituting here, simplifying everything. So other things gets cancelled. So finally left out with 8 by 4. So that is equal to 2. So it is proved that ratio of maximum velocity to average velocity is 2. So in university question paper, you will be asked to prove maximum velocity of laminar flow to average velocity is 2. So for which you need to show this derivation, this part of the derivation. Next, the last part of Hagen-Poiseuille's equation, so that is drop of the pressure over the given length of the pipe L here. So we have taken two sections 1 and 2. So the section 1 is at a distance of x1 from the left end of the pipe, and the section 2 is at a distance of x2 from the left end of the pipe. So now the distance between the two sections 1 and 2 will be x2 minus x1. So that is equal to L. Now we are taking the average velocity. So that is this. Then integrating this. So here we have del p in the equation. So rearranging the terms, taking dx to the other side. So we have del p left in the left side of the equation. So it is integration of dp with minus sign, and the integration limits are these two sections. So that is written here. So then integration of dp is p1 minus p2 here. So this is integration of dx. So that is nothing but here you have integration of dx is x. Substituting the integration limits 1 and 2, we are getting x1 minus x2, then minus is taken outside this bracket. So then this minus and this minus gets cancels here. So in the bracket left out with x2 minus x1, that will be substituted as x2 minus x1 as L here. So we are getting P1 minus P2 equation. So that is 32 mu u bar L divided by d square. So dividing both sides by rho g. So then we have in the right side, so 32 mu u bar L by rho g d square. In the left side we have P1 minus P2 by rho g. So that is nothing but the head loss due to friction. So P1 by rho g is H1, that is the head loss at the head at section 1. P2 by rho g is the head at section 2. By the time the fluid flows from section 1 to section 2, because of the friction in the pipe, so there will be energy loss. So that will be taken as head loss due to friction. So this is called as Hagen-Poiseuille's equation. Thank you, friends.